Welcome everyone. In this video, I'll be covering section 14.8 called Lagrange Multipliers. Another name for this section is the constrained optimization. The Lagrange multiplier is a method to find out the maximum or the minimum value of a function. So what is the geometric basis of Lagrange's method for functions of two variables? So you see certain curves in red color and one curve in blue color. The red color ones are level curves of a surface. So the surface is given to be z equal to f of xy, let's say. And how do you find out the level curves of this surface? This is a surface. Level curves are obtained by setting z equal to a constant, right? Horizontal plane. So you're finding the intersection of the surface on the horizontal planes for different values of k. So you're shown in the picture f of xy equal to 7, the level curve corresponding to k equal to 7 and k equal to 8, k equal to 9, k equal to 10, k equal to 11. These are level curves of f. Now you see another curve, one single level curve, which is g of xy equal to k. We have another surface called g of xy, and in that one you take a particular value of k and you take a level curve for that surface, different surface. So this level curve meets this level curve g of xy equal to k is called the constrained curve. Constraint curve. And this level curve meets the level curves of f of xy at several points. At one point, you notice it touches. There is one point at which the constraint curve touches the level curves of f. So let's see what the problem is right now. The whole goal is to find out the extreme values of f of xy, the maximum and minimum, but with a certain constraint. To find the extreme values of f of xy, subject to a constraint of the form g of xy equal to k, in other words, we seek the extreme values of f of xy when the point xy is restricted to lie on the level curve g of xy equal to k. The above figure shows this curve g of xy equal to k with several level curves of f. Okay, the pink ones, the red ones are level curves of f, and the blue one is a constraint curve. These level curves of f have equations f of xy equal to c. In the picture, it's shown c equal to 7, 8, 9, 10, and 11. To maximize f of xy subject to g of xy equal to k is to find the largest value of c such that the level curve f of xy equal to c intersects g of xy equal to k. So we are finding the largest value of c, the largest value of f of xy, such that the level curve f of xy equal to c, the largest value of f of xy, the level curve corresponding to the largest value of f of xy intersects g of xy equal to k. It appears from the figure that this happens when the two curves just touch each other. So at this point, wherever the two curves and the level curve of f of xy and the g of xy equal to k touch, there is a common tangent. This has a common tangent line. This means that the normal lines at the point If they have a common tangent, they should have same normal. This means that the normal lines at the point x0, y0, where they touch, are identical. So the gradient vectors are parallel. The gradient vectors are del f or nebula f, or so the gradient vectors, namely del f and del g, are parallel. If they are parallel, if two vectors are parallel, they are scalar multiples of each other. That is, del f at the point x0, y0, or gradient f at the point x0, y0 equal to gradient g at the point x0, y0 for some scalar lambda. The point at which the two graphs, two level curves touch is the point x0, y0. At that point, one is the gradient vector of f is a scalar multiple of gradient vector of g, and the scalar lambda is the Lagrange multiplier. So now let's explain the method of solving this problem or finding the maximum or minimum. So keep in mind, we are going to find the maximum value of the function f with the prescribed constraint. How the method of Lagrange multipliers works in finding the extreme values of f of x, y, z subject to the constraint g of x, y, z equal to k. Method of Lagrange multipliers. To find the maximum and minimum values of f of x, y, z, subject to the constraint g of x, y, z equal to k, assuming that these extreme values exist, that's important condition, and the gradient g is not equal to 0 on the surface g of x, y, z equal to k. A, find all values of x, y, z and lambda such that del f, the gradient f at xyz equal to lambda times gradient g or del g of xyz. Along with the constraint g of xyz equal to k. Then evaluate f at all points xyz, evaluate f at all points xyz that result from step A. The largest of these values is the maximum value of f. And the smallest is the minimum value of f. Note, the number lambda is called the Lagrange multiplier. In other words, the maximum or minimum occurs when grad f and grad g are parallel from step A. So these two vectors are parallel. When they are parallel, one is a scalar multiple of the other. So what is the Lagrange multiplier method to find out the maximum or minimum with the constraint? So find all values x, y, z and lambda such that lambda f equal to lambda del f equal to lambda del g, gradient f equal to lambda times gradient g along with the constraint g of x, y, z equal to k. So first to find out all values of x, y, z and lambda. Then evaluate f at the points x, y, z that you arrived from step A. Then largest among these is the maximum, the smallest is the minimum value. In the videos for this section, I have done the problems number 3, number 7, number 29, and number 40. All these are done using how to find maximum or minimum using Lagrange multipliers. So please take a look at these problems in the videos for this section. We'll try one problem here, which we have done in the earlier section, problem number 41 of the earlier section. We did the same problem by using the d-test earlier. But now we are going to do the same problem by Lagrange multipliers. Some of the problems that you did in section 14.7 can be done by Lagrange multipliers as well. Use Lagrange multipliers to give an alternate solution to the exercise from section 14.7. So I'm going to pick 41 because you've already done this problem or you have watched my video for this problem in the earlier section 14.7. Find the shortest distance from the point 2, 0, negative 3 to the plane x plus y plus z equal to 1. So this problem is going to be done now by Lagrange. This problem number here is actually number 31. 31 of 14.8 is same as 41 of section 14.7, done by Lagrange multiplier method. So the question is to find the shortest distance from the point 2, 0, negative 3 to the plane x plus y plus z equal to 1. So first let's start off with the objective function. Objective function is the one that you want to maximize or minimize. The question is the shortest distance between a point and a plane. So the shortest distance translates to minimizing an objective function. So let's find out first, let's write down the equation. The distance from this is step 1. Distance from the point 2, 0, negative 3 to the point x comma y comma z on the plane. So this is given by square root of x minus 2 the whole square plus y minus 0 the whole square plus z plus 3 the whole square. So the objective function is the one that you want to minimize or maximize. Because the question is to find out the shortest distance. The shortest distance translates to minimizing a function, minimizing the objective function. So what is the objective function that you want to minimize? So that I'm going to call as the square of the distance function, which is taking the square of the square root. So that becomes x minus 2 the whole square plus y square plus z plus 3 the whole square. Call it 1. This is the 1. Then what is the constraint? The constraint is the point, it is the point xyz must lie on the plane. So xyz lies on the plane x plus y plus z equal to 1. So this is the constraint. We'll call this one as 2. So you know the objective function now, you know the constraint. Now we are going to apply the Lagrange multiplier method. going to apply the Lagrange multiplier method, which is del f for the gradient of f equal to lambda times del g. Right? This is what we need to apply first. So del f stands for fx, fy, fz, partial derivative of f with respect to x, partial derivative of f with respect to y, and partial derivative of f with respect to z in component form. Lambda times del g, this is the partial derivative of g with respect to x, which is 1 from equation 2. Then again with respect to y, with respect to z for the function g. So this is our g of x, y, z. This is the constraint function. G of x, y, z equal to x plus y plus z equal to 1. So we get this result. So fx is, you have to differentiate the d square function. It is 2 times x minus 2 and then 2y times, I'm looking at step 1, then I'm differentiating that 2 times z plus 3. This is lambda times 1, 1, 1. Now you equate the corresponding components. So 2 times x minus 2 equal to lambda times 1, or 2x minus 4 equal to lambda, or x equal to lambda plus 4 divided by 2. So we got x. Similarly, we can find out y. So 2y equal to lambda. This implies y equal to lambda divided by 2. Then 2 times z plus 3. We are equating the corresponding components in this step. So lambda times 1. So this implies 2z plus 6 equal to lambda, or z equal to lambda minus 6 divided by 2. So we have got x, y, z, then substituting this information into the constraint. So this is the first stage. Then substitute x, y, z into the constraint function, which is x plus y plus z equal to 1. So we have lambda plus 4 divided by 2 in the place of x. Then similarly, y and z, if you substitute, you get lambda divided by 2 plus lambda minus 6 divided by 2 equal to 1. So we get lambda plus 4 plus lambda minus 6 equal to 2. So this will give 3 lambda minus 2 equal to 2, or 3 lambda equal to 4, or lambda equal to 4 divided by 3. So we got the value of lambda. Then from here, we can actually get the values of x, y, and z. So substituting this value of lambda over here, we can, from in here, we can get the values of x, y, z. So x, y, z. So if I have to give you one example, substituting lambda in x, which is lambda plus 4 divided by 2. We substitute lambda equal to 4 by 3 plus 4 divided by 2. So that will be 12 plus 4, 16 divided by 3 times 2. That will be 8 divided by 3. Similarly, y equal to lambda divided by 2. So it is 4 over 3 divided by 2. So that will be 2 over 3. Then z equal to lambda minus 6 divided by 2. So 4 by 3 minus 6 divided by 2. So this will give us negative 7 over 3. So we get x, y, and z. So we got x, y, and z. This x, y, z must correspond to the minimum. Eight by 3 and 2 by 3 minus 7 by 3 corresponds to the minimum. Or where the minimum is attained. So the shortest distance is D, where that x, y, z are replaced by 8 by 3, 2 by 3, and negative 7 by 3. So this is square root of 8 by 3 minus 2. We are looking at this first function now, the shortest distance. We are looking at this function. We have to find out the distance also. So substitute x, y, z into this. So 8 by 3 minus 2 the whole square plus 2 by 3 the whole square plus negative 7 by 3 plus 3 the whole square. So if you simplify this, it will become square root of 4 by 3, which is 2 over square root of radical 3. That is the shortest distance. So we have seen this same problem before. Now we are doing the same problem in Lagrange multiplier method. Hope this video helps.